Hello class, how are you? Hope all is well. The part 2 of this lecture is we're going now to look at file organization, the different types of ways in which files are organized on the disk. So we have the heap files. So we have the heap file organization. We have the sorted file organization. Sometimes the sorted file organization is called sequential, and then we have the hash file organization. But of course, what is in the different types of file organization? We have heap files, we have sorted files or sequential files, and then we have hash files. So what is the heap file organization? Remember, we said that when you're looking at file organization, you're looking at how these records are organized in the different files within a given page on the disk. So the heap file organization is the simplest and the most basic type of organization. Here, the records are placed anywhere in the file. So in other words, where there is space, that is where the records are placed. So there is no ordering of the records. The records are not placed in any particular order, okay? Wherever there is space, that is where the records are put. So the insertion of a new record is very efficient. Why? Because wherever there is space, that is where the record will be dumped. So, and the insertion of the new record is done in these following steps. 1, the last disk block of the file is copied into the buffer. In other words, we say in the last disk, we're looking at the disk that has, because you have numerous disks within your you have different blocks on your disk. And these blocks, the one that has a free space is where we're going to have our record dumped. So this disk block is copied into the buffer or the memory. A new record is added to that particular block, and then the block in the buffer is then rewritten back onto the disk. So that is the process. So in essence, if you look at here, let us assume that this is your what? This is your disk, where you have your different blocks that are going to house your records. So this you have these blocks. You have block 1, you have block 2, and then you have block 3. We are assuming that those particular blocks are filled with data. And then you have this block here that does not have data. This block is going to be copied into the main memory, okay? The main memory or the buffer. Okay, so this block, we are assuming it has been copied into the main memory. So a record is going to be added, or a tuple is going to be added to that particular block. After the tuple has been added to that block, then this particular block is going to be copied back onto the disk. So that is the process how the insertion of the new record is done in the heap file. So the same thing applies to if you're going to delete a record, if you're going to delete a record for that particular from that particular block. A block is copied into the memory or the memory buffer. The record is deleted, an update is done, or an update is done for that particular block, and then it is taken back into the disk or back to the secondary disk. So the search for a record is based on a search condition, which involves a linear search through the file block by block. What are we saying? That in the heaped file kind of organization, if you're going to search for a record, then you'll have to do a linear search. A linear search is where you search for a file block by block. You go on for in each the 4 blocks that we have that we saw. You go on searching for each and every particular block. You search for that particular record. So a block is copied into the memory buffer, then a search is done. If the record is not there, then it is copied back on the disk, then another block is brought put in the main memory, a search is done. If it is not there, it's taken back to the disk. So that is the process of the linear search. So we're saying that if only one record satisfies the condition, then on average, half of the file blocks will have to be transferred into the main memory before the desired record is found. So that is, we're just saying that in the event that it's only one record, you have only one record that you're looking for a particular condition. For example, you could have a SQL statement where say where you're looking for example, students whose ID number is equal to, let's say, 02 stroke U stroke. So if you're going to use that search condition where the student registration number is equal to this, with this kind of file organization, which uses a linear search, you will have to on average, okay, transfer at least half of the blocks into the main memory before you can actually get that desired record. So if no record or several records satisfy the conditions, then all blocks have to be transferred, okay? So in essence that we're saying that if one, you are not using a search condition, then in essence that means you have to transfer all the blocks to the main memory and then a search is done. So for you, if you're going to modify a record in a file, a program must, one, you have to find it, okay? That is now if you're going to do a modification. The process is literally the same. So you transfer that block containing the record into a buffer, okay? So you need to find that particular record. That's the program has to find. The operating system has to find that record. So the record is, you find that record and then a transfer is done into the memory buffer or into the buffer. Then the modification is done in the buffer. Then rewrite that block is rewritten back onto the disk or the secondary disk. As we have seen, the process of finding the record can be really, really time consuming, okay? So removing a record, still the program has got to first find the record, transfer the block that has that record into the memory buffer, delete the record from the memory buffer, and then it is rewritten back onto the disk. Again, the process of finding the record can really be time consuming. So, physical deletion of a record leaves unused space on the block, okay? So as a consequence, you will have a large amount of data, okay, may be wasted if we're going to have frequent deletions. So what we do as an alternative method is we have we put deletion markers on these records. So we're saying that an alternative is to physically deleting a record is to use one extra bit. That extra bit is what we call a deletion marker. So all your records will have a deletion marker. The deletion marker helps us to know what particular records were deleted and where they were deleted. So no matter what deletion technique is used, a heap file will require regular reorganization. So in other words, if you're dealing with a heap file, it doesn't matter what kind of deletion technique that you're going to use. If you're using a heap file, we will have to constantly reorganize our records in the file such that we can be able to reclaim the unused space that can later on be used by the new records that you're going to insert. So this whole file organization is kind of tedious in terms of insertion and searching for a record. So during such reorganization, the file blocks are accessed consecutively, and some records may need to be relocated to fill the unused space. So what happens here, because you have to constantly do this reorganization, it means that you will have to consecutively, okay, access each and every particular block that you have in your file, and then you reorganize, okay? But what does that mean? It means that some of the records may have to be reallocated and such that they can occupy the unused space. So an alternative approach to reorganization is to use the space of the deleted records when inserting the new record. So in essence, we're saying that if you don't want to do the file reorganization, that the other alternative, but at the end, we'll still have to go back in the same loop. We're saying that if you don't want to go through the process of reorganization and then having to, put the records to occupy the unused space, the alternative would be you leave the spaces, okay, such that the new insertions take up the space of the deleted records. You can also do that. However, this alternative will require extra facilities to keep track of the empty locations. So you have two options. There's the process of reorganization such that the records are taking up the new space, the space of the unused space of the deleted records. Alternatively, you can leave these deleted spaces such that the new records are inserted into the deleted spaces for the records that were deleted. But we say that if you're going to do this, okay, it's this kind of facility, really, this kind of approach requires you to have extra facilities, and this extra facility will have to keep track of all the empty slots that were deleted from the disk. So both the spanned and unspanned organizations can be used for a heap file. It doesn't matter whether the record is of fixed length or the record is of a variable length. We say that a spanned organization, kind of disk organization, is where you have a record and it does not fit on that particular block, but then it is moved on to the next block, such that part of the record is on one block and then the others are on the other block. That is what we call spanned. And unspanned is where you have all records are fitted within that particular block, and most cases it's used in fixed length records. So modifying a variable length record may require deleting the old record and inserting a new record, incorporating the required changes, because the modified record may not fit in its old position on the disk. That is, if it's a variable length. So if you're having a variable length kind of records, that means that where you have deleted the other record, the new record may not necessarily fit within that old position, implying that you will have to shift to another block. So let's take an example. Okay, we have we're going to see, we want to work out a few things. Let's assume that you have a file, and this file has 20,000 student records of fixed length. Each record has the following fields. You have the ID, which is 7 bytes. You have the name, which is 35 bytes. You have the address, which is 46 bytes. You have the course, which is 12 bytes. And level, 1 byte. The level of the level could be, it's an attribute there. So an additional byte is used as a deletion marker. Okay, we said that you can have in this file, you can decide to have a deletion marker to help us locate. It's like a pointer that helps us to locate the free slots that originally had data. So this file is stored on the disk with the following characteristics. The size of the block B is 512. The interblock gap size is that's the G is 128 bytes. The number of blocks per track for each and every, because remember the disk has what we call tracks. Okay, so we're saying that the number of blocks per track is 20. That means the hard disk has so many tracks, they are circular. So we're saying for each and every particular track you can have only 20 blocks. The number of tracks per surface is 400. So they're telling us to one, calculate the size of the record for that particular file. They're telling us to calculate the blocking factor, that is the BFR. The BFR, we said that this is the number of records that can be stored on the block. Then they're telling us to calculate the number of file blocks needed to store the records, assuming that these records this being a fixed length record, it means that the file organization is unspanned. So what do we do? This calculation can be they want one to calculate R. R, remember, is the size of the record. and then we have, that's R, and then also they want us to calculate BFR. BFR is the number of blocks, and then they want us also to calculate BFR. This is the BFR is records in the block. And then we have the B, which is the number of blocks. Number of blocks. So that is what you need to know, what each and every. So the R, that is the number of blocks. So looking at the other example, they said that the size, the record size. So if we go back here, if we go back there, the R is equal to 20,000. So these are we have R, which is equal to 20,000. But this is the small r. So the big R, we have to count the bytes for each and every particular field. So ID is 7, name is 35, address is 46, course is 12, level is 1, but we need a deletion marker as well, which is 1 byte. So when you add these different bytes, it's going to give you the size of the record. Okay, so in this case, if we go back here, so in this case, R, which is the size of the record, R, which is the size of the records, is the other, the 35 plus 2 plus 7 plus etc., which is equal to 102. So that means this particular, the records that are in this file, okay, are 102 bytes. We have added 12, 7, 32, 35, and 46. That's the size of the record. And then calculating the BFR, okay, calculating the BFR, you said BFR is the records in the block. So the records in the block is equal to, the formula is B divided by R. That is the B, that is the size of the block, and then the R, the R is the number of, sorry. Okay, I just want you to, B is the size of the block, and then R, the capital R is the what? Is our record size, which you have already got there. So the size of the block in this case, it was 512 divided by 102, and then we get 5. Okay, so what does this 5? These are the records per block. So with 5, for each and every particular block, you're going to have 5 records. That is the BFR records in a particular block. So this is the B. We were already given the 512. Then calculate the number of file blocks B. Now the small b, they're telling us the small b. The small b is the number of blocks that you need, okay, to store the records. Remember that the records we have already, they are 20,000 records. So where they're asking for the space, how many blocks will you need for you to store the 20,000 records? So we go back here, which is the number of blocks, and we say that, how do you compute that? It's computed as this B, no, this small b is computed as the number of records, okay, the other number of records, which is equivalent to the small r, okay, and then you divide it by the BFR. The BFR that we have already, the BFR is the number of the records in a particular block, okay? So that is what you divide by the BFR. So we are looking at the records that we already have, and then the records, and then we divide it by the records in a particular block. So this, remember we said that 5, those are the maximum number of records that you're going to store in a block. So in instance, the 20,000 records that you have, you divide them by 5, this 5 that we already computed, sorry, and then you get a 4,000. So what does the 4,000 mean? The 4,000, these are the number of blocks that you're going to have to use to store the 20,000 records. This is the B, the small b, this number of blocks. You need 4,000 blocks to store 20,000 records. So that is what? That's what it means, and that is how we do the computation. Then okay, so we have studied how records are represented in a file structure. A relation is a set of records. So given a set of records, the next question is how to organize them in a file. Okay, and the different the files that we have, the different file organizations, we have said we have a heap file organization. I've shown you how. Then we have a sequential file organization, which is what we're going to see next, and then we shall finalize with a hash file organization. So a sequential file organization, this one from the word sequence. So it is sequential file, or sometimes it's called sorted. So the records are maintained in a logical sequence of their primary key values, okay? So in a particular order, sorted in a particular order. So the process of sequential filing is it's conceptually simple, but sometimes it is a bit inefficient, especially if you're going to have random accesses. So a sequential file could be stored on a sequential storage device, for example, a magnetic tape. Searching for a given record in a sequential file on average will require you to at least access half of the records of the file, more or less, you know. So on average, access to half of the records in that particular file if you're going to use a sequential file organization. So a binary or a logarithmic search technique may also be used to search for a record if you're going to use sequential file organization. So updating usually requires the creation of a new file. To maintain file sequence, the records are copied to the point where the amendment is required. Then remember, everything has to be, all these, the amendments that you're going to do on your file, they have got to be sequential. So the changes are then made and copied to the new file. Following this, the remaining records in the original file are copied to the new file, thus creating an automatic backup copy. So let's take this example, okay? We're going to have this as an example for okay, it's kind of all right. So the following figure depicts a sorted file organization containing student records. Why do we say it is sorted? If you look at the ordering key, okay, the ID number, it is sequential all through the different blocks. So if you're going to use a binary search algorithm for this particular kind of file, we're saying that a binary search for the disk files can be performed on the blocks rather than on particular records. So in this case, you are looking at a particular block rather than looking at an individual record. So the file has B blocks, that is, it has the blocks, those are the number of blocks, 1 up to block B. And these records are ordered in ascending order by the ordering key, just as you see. So when you're searching for a record whose ordering field value is K, for example, the disk addresses of the file blocks are available in the file header. We're saying that this particular file has all the disk blocks for each and every particular block. The disk blocks are in the file header. Remember, we say the file header stores the addresses of the different disks. So a search algorithm is, let's look at this pseudocode and how this whole thing works out if you're going to use a binary search. So if you look at this pseudocode, okay, this pseudocode is just to tell you how the search is being done or how the search will be done. So essentially what happens is a binary search always begins from the middle block. Why do we say the middle block? Because it's a binary search. So it looks at, now if you go back here, sorry. So what it does is it will always, because being binary, it divides the blocks, and the one that comes in the middle is the one is the one that is going to be copied in the memory buffer. So it starts the search here. So let us assume that we are looking for a record that is 970 1890. This is the record K that we are looking for, 970 1890. So what happens in 970 1890? The file, the program is going to copy this disk, because being a binary search, I say that it divides, and then the block that happens to be in the middle is the one that is copied into the buffer. So this is going to be copied into the buffer. And then a search using the ordering key is going to be used. So this ordering key. But remember, we are looking for 970 1890, which is equivalent to K. Okay, I wanted to use the pseudocode, but let's use the live records here. So when the search is done to this particular block in the buffer, being that this is a sorted order, then the program will realize that the search will realize that the actual buffer, the actual record that we are looking for, which is 970 1890, cannot be in this block, because this is 970 335,001, implying that this has got this block well copied back onto the disk, and then we shall take disk block 2, because block this happens to be higher than what we are searching for. So block 2 will be copied onto the memory, a search is done, and then looking at the ordering field, block 2, the search realizes that the first record in block 2 is 970 2381, which is greater than 970 1890. This will be taken back to the disk, and then block 1 is going to be copied onto the main memory, and then a search is done, and then this record is going to be found there. So that is what we call a binary search. If the search was looking for 244 990 244, still it would have taken the middle block, copied it into the memory, search is done, it realizes that no, this particular record we are actually looking for is greater than the last ordering key of this last block. So what happens is it takes it back to the to the disk, and then this disk is copied onto the buffer, and then when they do the search, this particular record is formed. So that is how the binary search works out. And so this explanation is just to explain this pseudocode, which also this is the same as what I have just explained. So the advantages of a sequential file: 1, it is easy to access, ease of access of the next record, simplicity of the organization of records. Reading the records in order of the ordering key values becomes very efficient because of the sorting that happens. There's absence of auxiliary data structures. In other words, to reduce on the cost per update, all the updates are batched up together, and then a file is sent in one go or in a single pass, and then an update is done. So with this, that they don't have those issues of you having to update a single record. And then 5, the retrieval using a search condition based on the value of the ordering field can be very efficient when a binary search is used. Hence, a sequential file is designed for efficient processing of records in sorted order based on the search key. So you'll find that this is at least much better than the first file organization, which is unordered, because we say that with unordered, it has to use what we call a linear search, where each and every particular block has to be copied to the buffer and then searched and then a search is done. So the search key is any attribute. Remember, the search key doesn't have to be a primary key. It can be any attribute. It could be a set of attributes that you're going to use as the search key. So to permit fast retrieval of records in the search key order, we chain together all the records by pointers, and then the pointer in each record points to the next record. With the pointers, like how I was explaining how I was explaining this thing. sorted. So that is how you should look at it, that each and every particular record points to another record and another record, and so on and so forth. So furthermore, to minimize the number of block accesses in a sequential file ordering, we store records physically in a search key value. So that helps us in minimizing on the time that you're going to use to search for a particular record, and then therefore it also minimizes on the number of accesses that you're going to use, that you're going to have to go through for that particular block. The sequential file organization allows records to be read in a sorted order. So it is difficult, however, to maintain the physical sequential order as the records are inserted and deleted. It becomes a little hard for you to, because records are inserted in, they are deleted. So keeping that sequential order becomes a little bit tedious, okay, and very costly. So this can be managed using pointers. At deletion, you have a deletion marker, and you have also an insertion marker. This is how you can try to manage that. So the performance issues, the sorted file organization can offer a very efficient retrieval performance only if the search is based on the ordering field. Okay, that's the only performance, that is the only advantage that you're going to get. That is if the search is based on the ordering field. For example, you see here, you're saying select name address from a student where the ID number is equal to this. So the ID number is not in the condition. Sorry. So because the search condition has specified the kind of search that we want for this particular record, okay, it becomes a little bit simple to retrieve that record. However, if the ID is not in the condition, if you're not doing this, that means that you're going to perform a linear search. And we said that a linear search is very tedious, it's very expensive, and also it kind of compromises on the performance of the database. So update operations, that is the insertion and deletions, are very expensive on an ordered file because you have to follow that order, the order of your files that are in sequence. So one option for making insertions more efficient is to keep some unused space in each block for the new record. However, once that space has been used up, of course, the other problems are going to be the initial problems. We're going to face them. So in the sorted file organization, it is rarely used in databases unless you're going to use index structures in terms of accesses, but otherwise they are rarely used. So the second exercise is we're going to try and calculate the average number of block accesses needed to search for a record with a given ID number if you're going to use a binary search, okay? So if you're going to use a binary search, the equation is, we said it's a log2 binary logarithm. Where could I get the symbol? Okay, let me just do it here. log2 b. Okay, it's a b. Remember, we already have our b, the number of blocks. Okay, the number of blocks. And what are we looking at? We want to calculate the number of block accesses. Block accesses is how many blocks can you access if you're going to use a binary search. That is what we are looking out for. And this is the formula, the binary logarithm and the b, which b we already have. So in this case, we are going to have 4,000, and the binary log 4,000 will give us 12 block accesses. So in essence, for this particular, if you're going to, because they're saying we're using the same example, if you're going to use a binary search, it would mean that you're going to for you to search for a record, you're only going to access 12 block accesses. Unlike here, okay, where if in the unordered file where you're using an unordered file where you are using a linear search, it means that you will have to go through all these 4,000 records in the linear search. But in the sorted, where you're using a binary search, you only have to go through 12 block accesses for you to get the record that you are searching for. So you realize that there is an improvement in performance from the linear search that is using the unordered to what we call a binary search, where you are in the sequential file organization. So the performance keeps increasing. So we go to hash file organization. Hash file organization, the hash file organization is based on using a hashing technique. So you have a hash field, okay, which is also the key field. And the key field is the one that we are going to use to search for the records. So the search condition must be an equality condition on a single field, which is called a hash field. So for example, this could be your hash field or the hash key. So the hashing technique, the principal idea behind this hashing technique is to provide a function, okay, which is a hash function, which is applied on the hash field or the hash key of a particular record, and it computes the address of the disk block where that record is stored. So you have a hashing function. Okay, this hashing function is applied to your hash field. For example, this could be your hash field. Then after it does compute for you the address where the disk block is for that particular record that you are searching for. So again, here now you realize that now the searching is becoming more and more easier and more narrower, because now here you are going to get the actual disk where the record is found, unlike in the unsorted, where you have to look through all the disks, unlike in the sequential, where it will give you an average of the disks that you're going to search for. But here it is giving you the exact disk where the record is stored. So for most records, we need only one block transfer to retrieve that record. And this is now the advantage of using the hash file organization. So we're giving an example that, okay, suppose K is your hash key value and the hash function H is mapped onto that particular value. So the following takes place. So you have this function K, okay, that is the address of the block containing the record where the key value K is. So this is the function, and that is the function that is going to apply on the field, and we shall be in position to know the exact block where that particular record is stored using that hashing function. So if a hash function operates on numeric values, then non-numeric values will have to first be transformed into numeric ones before the function is applied. So that's the standard, implying that we need to have numerical values as our hash key. So the following are the two examples of many possible hash functions. So for example, you have a hash function, okay, mod m, okay. This function returns the remainder of an integer hash field value k after division by an integer m. The result of the calculation, okay, so when we say this particular hash function, mod, okay, hold on. I'm trying. Mod function, sorry, using the mod for us in the hash function. What this means is we have a technique in hash function. It's called division remainder hashing. Division remainder hashing. So this technique uses the mod function, which takes the field value, okay, it divides it with some predefined integer value, and it uses that remainder of this division as the disk address. So for example, if we go to this next block, so this next slide, what are we saying? We're saying, I'm trying to explain the mod. The mod is, For example, you could have like 43. This is just an example. You have a hash function k mod 7. Okay, remember we said that integer, it's the predefined integer that you use to divide with the other blocks. Okay, or that is going to be hashed to the other blocks. It's just an integer that you're going to pick to divide. It doesn't matter. So when you pick that integer, you're going to divide it with I'm trying to explain the mod function. So you're going to divide it with your block accesses. So the remainder that you have is what, in other words, it is telling you that the record that you are looking for is in block 1. But this has a challenge. But let's just first go through this. So the mod function is saying that a different function may involve picking some digits from the hash field value. You can pick a digit, let's say a second digit, you can pick the 4th digit, you can pick the 10th digit, whatever it is, from the hash value. The hash value is the key that you're going to use, okay, to form an integer that you're going to use to divide, okay, to form an integer that you're going to use to do the division. So what happens, they're saying that the problem with most hashing functions is that they do not guarantee that distinct values will hash to distinct addresses. The reason is that the hash field space, that is the number of possible values a hash field can take, is usually much larger than the address space, that is the number of available addresses for the record. So for example, if a hash function k mod 7 will hash 15 and 43 to the same address 1 as shown below. So in instance, if you divided 43 with 7 and 15 with 7, it means that this particular function is going to give us the address 1. But remember, 43 could be a different disk address, and then also 15 could be a different disk address. But because it uses what we call a division remainder hashing, that the remainder, when you divide, and the remainder that you have is the one that points you to the block where that record is, or points you to the block where you will do the insertion from. It means that you might experience a collision, okay, because of using this particular hashing function or hashing technique. So a collision occurs when the hash field value of a new record that is being inserted hashes to an address that already contains a different record. So this particular, if you say pointing to address 1, the block 1, and also you do another hash function and then it takes you to 1, it means there's going to be a collision. It is going to take you to a disk that already has the records. So that is the challenge with using the hashing function. So in this situation, we must insert the new record in some other position. And the process of finding that other position is called collision resolution. So I've said that the challenge of the hash function is the one that uses the mod function is in the process of dividing, it will, if you divide and the remainder is 1 in the particular hash function, and then the next time you want to add a record or search for a record, it also gives there's a 1. It means that you're going to have, or you're going to experience, a collision. So how we address, so when the process of finding a new position is called a collision resolution. You want to find a new place and then you avoid the collision. So the following are commonly used techniques for collision resolution. 1, we have open addressing. If the required position is found occupied, the program will check the subsequent positions in turn until an available space. So in other words, if we wanted to insert a record in a particular position and we find it when it is occupied, then we will have to find the next position and the next and the next and the next until a space is allocated. That is number one. The other way of dealing with this collision is chaining. For this method, some spaces are kept in the disk file as overflow locations. So in addition, a pointer field is added to each record location, implying that you have a pointer that points to the location that is empty or that has not been used. So a collision is resolved by placing the new record in that unused overflow location and setting the pointer of the occupied hash address location to that particular address of the. So you set a pointer and for that particular record that you have inserted into the unused space, so such that that particular record is not pointed to as an empty record. That's why we have those pointers. So in this case, you're going to have a linked list of overflow records for each hash address. I explained to you a linked list in the previous video and how it works. So you're going to have a linked list. So you have you have a pointer that points onto the other another record and also points to another record. So that is what we call a linked list. So we have a multiple hashing. If a hash function causes a collision, a second hash function is applied. So we're saying that multiple hashing. Now, if the other one caused a collision, then you might have to do another hash function. If it still causes another collision, then we can use the open addressing. The open addressing, remember, we said that you look out for a location. If that field if that record is filled, you go to the subsequent and the subsequent until you find one that is free. So each collision resolution method requires its own algorithm for insertion. For each collision resolution, it will require its own algorithm for insertion, retrieval, and deletion. The goal of a good hash function is to distribute the records uniformly over the address spaces and minimizing the records, but at the same time, not leaving any unused space in the disk. So the hash function should not involve complicated computing. Otherwise, it may take a long time to produce a hash address, which will actually hinder performance. So in essence, we're saying that the hash function should not have complicated computing, or it should not be as complicated to compute the address where we want to get the record or where we want to store the record. It should be as simple as possible. Otherwise, it will compromise on the performance of the disk. So we have external hashing. Hashing of the disk file is called external hashing. To suit the characteristics of this storage, the hash address space is made up of buckets. Okay, each and every particular bucket consists of either one disk block or it has a clustered number of blocks together, that is in a bucket, and all these can accommodate a certain number of records. So a hash function maps a key into a relative bucket address or bucket number rather than assigning a particular address on the entire block. Okay, so a table is maintained in the file header that converts the relative bucket number into the corresponding disk addresses. So this is what I am talking about if I borrow this illustration. So you have, we're looking at external hashing. So you have, this is your directory. So the directory has The first block is 001, the second block is 002, the third block 10, 11, 100, 1, 0. So each and every this directory corresponds to a particular bucket. This block corresponds to a particular bucket. This one corresponds to a particular bucket. So if you look at the bucket for records whose hash values start with 001, so that means that for all the records, okay, that have the hash value starting with 001, they are going to be in this bucket. So you have this corresponding to that. For all records that have the hash value starting with 001, they are going to be in there. For 010, 11, 100, 01, etc. So that is the arrangement and how the buckets, so you know that all the records are stored in form of buckets, and all these buckets have their addresses that are tagged. So if I am looking for a particular record that is 111, the hash function is going to be put on this 111 such that you only have this particular bucket that is going to be copied into the disk for you to search for that particular record that you're searching for. So that is that's what it's the explanation of the hashing function using external. So the dynamic hashing, some hashing techniques allow the hash function to be modified dynamically to accommodate the growth and the shrinkage of the database. So dynamic hash functions is where you can constantly play around with the hash function, because the database will either grow or it will shrink. So you also have to be dynamic enough to make sure that the function also accommodates that shrinkage or the growth of the database. So performance issues. Hashing provides the fastest possible access for retrieving a record based on its hash function. However, the search for a record where the hash field value is not available is very expensive. So if you're not going to have a hash field in that particular search, then it's also as good as a heaped file when you're going to search for that particular record. So the drawbacks of the hashing technique is the number of buckets is fixed, but the size of the database may grow. So you may have this number of buckets that we have 1, 2, 3, 4, 11 buckets. It is fixed, but what if the database grows? It means that you're going to have some issues. Also, if we create too many buckets, a large amount of space may be wasted. You can create so many buckets, and yet these spaces may not be used, okay, may go unused. That is also the other drawback. And then we're saying that if there are too few buckets, collision will occur more often. Again, if you create the buckets and there are too few, you will face the collision problems. So it's about playing around with the hash function. Make it a bit optimal. Not too many buckets, not few buckets, and so on and so forth. So this is an activity, record deletion in extensible hashing. So you will work it out. You'll find this in your I'll upload it on your learning platform such that you'll be able to read about deletions in extensible hashing function. So that's the end of this video. Bye-bye.